everyone. Welcome back to the Lion's Den. Today we speak with Jeff Jensen, who is the co-founder of a company called Xronos. Now, Jeff is a technologist in the purest sense of the term, and he really knows a lot about all trends going on in the tech world. So we talk about artificial intelligence, we talk about robotics, we talk about the challenges of writing software for robotics, we talk about self-driving cars, we talk about brain chips that can allow you to control your body or control screens and things in front of you. Really fascinating guy, and we get through a lot. So you're going to enjoy this one. Check it out.
So Jeff, I'm super excited to have you on the podcast today because I was looking at your LinkedIn page, and I don't know how you got to be able to do all these crazy things that you're doing from like a technology perspective, but I'm very interested in many of them and would love to dig into those. And then of course, understand like towards the end, how someone even goes down that career path. It seems really crazy, but let's maybe start at the top. So let's just talk about like what you're doing right now. That company is called, is it Xronos? Is that how you'd say that?
Yes, that's right. Yeah.
Okay. So what is Xronos? What are you guys working on?
Yeah. Well, first, thanks for having me, Nico. Great to chat, and I've enjoyed the content you've been putting out. So yeah, Xronos is trying to solve a problem that I've seen throughout the different stages of development of robotics throughout my career, which is it's very hard and very expensive to build robots. The promise of robots has been around since the 1960s, hasn't yet materialized in the way that we maybe had envisioned. And part of that is that the software for developing robotics is really difficult. It's difficult to write software that is aware of physical time, and it's difficult to write software that can do multiple things at the same time very predictably, which is what you need when you're controlling a physical world. So we're building out a lot of the infrastructure, the pieces of that software that would be useful everywhere from industrial automation to robotics to drones to autonomous vehicles, where you can get reuse of that technology. And we're productizing research that came out of the University of California at Berkeley, which has been backed by major industry sponsors and started to get a lot of momentum. And so we're working to commercialize that initiative.
Awesome. And you, on your LinkedIn page, so you also went to Berkeley for undergrad and your master's, right?
That's right. Uh-huh.
Okay. And so you said research from Berkeley. So was it like a student, or it was like faculty plus student, and they came to you guys to help commercialize it? How does that actually happen?
Yeah, it's a deep history, and it was, in fact, the research group, which I was a researcher with back when I was in university. I've stayed in close contact, but it's a research consortium called the Center for Industrial and Cyber-Physical Systems. Cyber-physical systems being a very technical term for anytime you have computation, communication, and control of some physical system. And the research of that organization has been funded by major industry players like Siemens, Bosch, Toyota, Denso, United Technologies, and others. And so, and they were all industries who were facing these same types of problems of how do you write software that controls these physical systems, and it's hard. And so that research has been ongoing for some time. A project came out of that group. And so it's a consortium of many different researchers, not just one student or professor. The group was led by Professor Edward Lee, who was the former chair of electrical engineering at Berkeley and also my former advisor. But it's a large research group who's been there. And so it was researchers across many different institutions across the world, both academic and industry, as well as students. And about 7 or 8 years ago, one of those projects started to get a lot of momentum. And happened to be the right time for me to also join and start a company. And so I took the lead developers of that technology, which is now Xronos's spearheaded technology. And that's where the company got started.
Okay, awesome. And so how far along are you guys? Like, do you have, you mentioned a bunch of different like use cases for the software, like manufacturing and different things. So have you guys gone to market yet with software? Do you have like certain types of customers?
Yes, we've been able to move very quickly. We do have a product out. So if you actually search the name Xronos, you'll find the first product we have is a Python library for interfacing with robotics. And it's in use in the automotive space. And it is also currently in use in food technology, as it turns out. It was just a coincidence that I've worked in that in the past. But some of our first customers are working in automated production of food and commerce areas. And so we've seen a few different industries already start to pick it up, which is a great sign because we just got started this last year. So it's really pleased to see the momentum happening so quickly.
Okay. So when you kind of described the complication of writing software that can then interact with the physical world, I always think of like in movies where somebody opens up the head of a robot and you pull out the brain and it's like some gelatinous thing with like electrons going through it or something like that. I guess they do it that way in the movies because nobody has really solved it in real life. What is it actually like in real life? Like, how are you solving that problem that you're describing?
Well, that's a great question. I think that the gelatinous brain question is still a very relevant question, and AI touches on that a lot. The way that we're solving this problem is much more fundamental. Traditional programming languages were developed to process information, to do things like write a request and response and get an answer from a dictionary or a database. They weren't really designed to deal with physical time. And what you care about in like a car or a robot is that it not only does it get the right answer, it has to get the right answer at the right time. So just because your car braked doesn't mean it got it right. It had to brake before it impacted something. It has to process the camera, where a lot of cars already in the market have predictive braking, and their camera or radar detects an obstacle, they'll brake for you. I've been in a vehicle that stopped because of this before. And if you detect the object successfully, but you don't brake in time, it made no difference. And so that's a really hard problem to get right. It requires expert knowledge of all of the pieces of hardware, the computers, the sensors, and you have to write software that knows how to do something at a very specific time. And that's just not something traditional programming languages were designed to do. And so that's where the research came out of Berkeley, was developing the types of programming languages and orchestration languages with very strong mathematical underpinnings, with provably strong behavior and predictable behavior that allows you to make such strong statements when you're developing a robot. This will happen at a certain time. If it doesn't happen in time, go to a fail-safe mode. And to make that much easier to do, especially when more than one thing is happening at the same time. That's really the key differentiators, that we're adding that kind of mathematical rigor and determinism and repeatability to the programming languages we were already using.
Gotcha. Okay. And when I asked you, use cases you have in play right now, and you mentioned, food, and then you mentioned automotive, I thought you were talking about like the robotic arms in automotive manufacturing, but you're talking about like self-driving cars you guys are working on.
Actually, both. We are actually working with both. We are working with the manufacturers of the arms that are used in the manufacturing of automotive, and we're also working with, I wouldn't necessarily say autonomous vehicles. That's a certain more narrow sector of it. The direction you're seeing go here is what they call software-defined vehicles. And this is a trend you're going to see across lots of different industries, is that once you have behavior that can be upgraded by a software update, like we saw Tesla do, who is a leader in the space, now you've got behavior of a vehicle that can be changed by software. And so they call that software-defined vehicle or software-defined hardware. And those are, according to Andreessen Horowitz, a huge area of innovation for 2025 specifically that they're investing heavily in, is taking a sector like hardware for robotics, which maybe hasn't innovated as much. Robotic arms have been around for a while, but now that you have more software-defined characteristics that can improve over time without needing to replace the hardware, your machine vision algorithms got better, your AI got better. Now the capabilities of my car or my robot improved. Tesla was able to release more autonomous-like driving characteristics of the vehicle and behaviors of the vehicle without you having to take it into the shop and change any part out. And so there's a huge advantage to being able to innovate in the marketplace when you have the capability to be more software-defined in your behavior. And so this is a trend that you're going to see in autonomous vehicles, but in a lot of other sectors that touch hardware as well.
Okay, interesting. I know that with autonomous vehicles, the data is pretty clear that like they reduce wrecks and fatalities and injuries and all that stuff by like a pretty dramatic margin. So I don't even think that that's like controversial anymore. I think that's just fact. But but how close do you think we are, like by your estimation, to having something with self-driving vehicles that is like such a no-brainer and so accepted by everybody that they're just all over the road and we start to phase out human driving? How far do you think we are from that?
That's a great question. I think we're there now, personally, from a technology standpoint. That doesn't mean that the technology is done. But if you put it in the right guardrails, in the right use cases, if you kind of do the classic startup mantra of do things that don't scale, so you have a lot of teleoperation, which all of the autonomous vehicles out there currently do have, then you can start to get pretty far. And then once you're in the marketplace, you're learning at a faster pace. So I think we're at a place where right now, I would trust autonomous vehicles in the right kind of fenced-in spaces more than I would trust human drivers in many cases. There's a big societal problem with this, which is research will show that humans are much more likely to trust human decisions, even though they're less reliable. Humans might make a different decision if they're tired, if they're upset, if they got in a fight with their spouse that morning. Robots don't do that. Autonomous systems don't do that. And so even though autonomous systems make very consistent decisions, our human nature is not to trust them. And I think that's the major hurdle. I do think, though, we have to temper expectations as to what those guardrails are for where the technology is ready. One of the best blogs I've ever read from a business standpoint was from the founders of Starsky, who did the first ever fully autonomous semi-truck that crossed the country. And this was this is maybe 10 years ago at least. And the company went under, and super smart people behind them, and they're still working in the space. And they basically said, hey guys, this problem is a lot harder than people think. This is not a 5-year point where we're going to have autonomous vehicles everywhere. There are a lot of technology problems that make this really, really hard to solve. So trusting an autonomous vehicle on a highway through most of it is doable. End-to-end last mile, where there might be pedestrians and animals in the street and changing conditions, that's still going to be, I think, another 5 or 10 years before you're seeing widespread adoption of end-to-end autonomous vehicles.
Okay. And then you add on the regulatory hurdle, and you may have cities and states banning it in their areas and whatever.
Yeah, and I've met with the directors at NHTSA, the National Highway Transportation Safety Administration, and who were in charge of certifying and approving these systems. They necessarily kind of have to go slow, as any regulatory body does. I think of any kind of regulatory body that I've seen, they've actually been one of the more forward-thinking and more willing to work with the manufacturers. I've seen that to be a much slower process in nuclear or in med device. And so regulatory is a major factor, and you're not going to work around it. So you have to engage with the regulatory bodies when you're doing something entirely new.
Yeah, makes sense. What about timeline on like humanoid robots actually in our everyday life? How close do you think we are to that? That's obviously something, it seems like you're working on the software that would enable that, right?
Yeah, it would definitely be something that would accelerate the development of a humanoid robot. It's interesting. There's so much fervor behind humanoid robots right now. I've seen, and do analyst calls with major financial institutions who are looking to determine whether they should be investing in the sector. They're hot on it. Hedge funds are hot on it. Startups are hot on it. Startup investors and VCs, if you look at VCs portfolios, they're also talking about it a fair amount. I don't know that I totally understand why there's that big excitement. There tends to be just bubbles, but bubbles can move things. And so there's investment happening in it right now. Humanoid is exciting because you can take a humanoid and put it into a system that was already designed for a human, like a kitchen or a work cell in a manufacturing plant where a human was already centered around that work. And so you don't have to retool everything around. They can use the same tools, the same workspace, and presumably be drop-in replacements. That's the attraction of it. I think that the hardware is not the problem. I mean, getting costs down is a good thing. The sensing technology is getting a lot cheaper. So LiDARs, high fidelity radars and other types of sensors are getting really good for robot to be able to perceive what's around it, which is important from a safety perspective, but also to be able to adapt to the environment as it changes. The problem is AI. We just don't have the algorithms yet that are sophisticated enough for a robot to be able to handle new scenarios that it's never seen and never trained for, and to make the kinds of inferences that our squishy human brains are good at making. And that's why when you see in the movies and they pull the head off the robot, it's a squishy human brain, because right now we don't have technology that looks like what a brain can do, and that's adaptability. And I think that there is still a gap there that we need to close. You know, LLMs were clearly a massive step forward in AI, and but then a very specific type of AI where it's able to train on existing things and then just kind of generate responses. It's not good at perceiving things in the physical world. It's not good at inference or applying rules of logic. It doesn't have that. And so you're going to need some type of significant advancement in AI algorithms in those areas of perception, akin to what happened with LLMs, before you see humanoid robots be truly capable of being a drop-in replacement for a human.
Okay, that makes sense. Yeah, like if you just ran ChatGPT on a humanoid robot right now, it's like they could answer questions, but if you wanted it to actually do something intelligently, I guess that technology is not really there yet.
It's exactly right. And the problem of hallucination with LLMs is also a problem where it's just predicting the next thing to say. It doesn't actually know if it's right or wrong. And there's never a way of testing that. And so, and there is work to apply LLMs to some robotics applications. Maybe that will be fruitful. It's still early, but I suspect it's probably entirely different approaches to machine learning that will ultimately result in the high growth and capability that will get you where you want to be.
Got it. Okay, let's go to a role that you held at a different company prior to Xronos, and that was BlackRock Neurotech. And so that was brain-computer interface. And so I think most people have heard of like Elon Musk's Neuralink, and obviously there's a lot of work being done there. So what is this technology? How does it work? Because I have not like read about it at all, really, aside from like, hey, look, this guy was playing video games with his brain. How does this work?
Yeah, well, I mean, I think anecdotally, the is something like that. In fact, I just yesterday had the privilege of speaking with a friend of mine, Ian Burkhart, who leads the Ian Burkhart Foundation, as well as the Brain-Computer Interface Pioneers Coalition. And Ian is someone who himself had experienced a spinal cord injury and is what would be categorized as quadriplegic or tetraplegic. And what this technology is it's a neural implant. And Ian was one of more than 70 recipients of the specific technology that BlackRock developed, that after receiving the implant, it's able to detect intentions to move in your brain. And we're able to understand those intentions in a computer and then use them to affect the world somehow. Control a mouse cursor on a screen, or in the case of Ian, we were able to, or the researchers, this wasn't our project, this was through a research organization, but apply a sleeve on his arm that was able to electrically stimulate his hand and wrist so that he was able to play Guitar Hero by entirely thinking about moving his hand. So he's the first person to have ever recovered the movement of a paralyzed limb. And this could extend to exoskeleton technology to help people recover walking and movement. This can scale to even just controlling a mouse cursor on a screen is a really big deal because it allows for more effective communication and engagement on the internet and recreation. And honestly, playing a game with your mind is a really big deal because it's not something that could be done independently by a lot of individuals who are paralyzed. And in fact, even with Neuralink's first human implant, that's one of the first things they showed is they said, hey, I was able to play a video game all night. And that's so amazing. And I'm so glad for that. But that's what the technology does. And Neuralink certainly has the high visibility that Elon Musk will give to a company. And so people have heard of it. But almost anyone who is at Neuralink, who has done research in human implanted brain-computer interfaces, will have used the technology that was developed by BlackRock Neurotech. So BlackRock has really set the foundation for what brain-computer interfaces can do from an implanted technology. More than 150 peer-reviewed journal articles, with human research, 60 or 70 patients implanted, patients with more than 10 years of operation with the technology and still going, and probably 40,000 plus patient days of data and research of using these brain-computer interfaces. I'll give you one other example. If you've ever known anyone who was affected by ALS, Stephen Hawking was someone who was well known to have had the disease. In fact, the longest living person ever to have it. It's a really devastating diagnosis, and it's certainly going to be a terminal one, where you lose effectively the ability to communicate at some point. If you can't control your muscles, you can't blink, wink, you can't give any indication externally of an intent or an answer to a question. And at that point, when they call that locked in, you've lost the ability to communicate to the world. And with BlackRock Neurotech's technology, with that implant, these individuals have regained the ability to communicate. And there's not a large sample size, but in the small number of people for whom this has occurred, the first thing that they say inevitably is, "I love you," to somebody. And that's a really touching moment. Now, there was one exception. There was a gentleman in Germany who received not BlackRock's technology, but a very similar technology. And the first thing that he asked for was if someone could play the Tool album he had been wanting to hear for a long time.
Well, he's German, so love isn't usually the first thing that comes to mind for them.
Sounds about
right. One of the crazy things you just kind of outlined was that sleeve thing. So you said he put the sleeve on, and the sleeve was able to electromagnetically, whatever, stimulate hand movements. I mean, could you put like an entire body sleeve on eventually if the technology evolved, and basically it's just kind of like an external nervous system is what you're putting on, right? You're still plugging into your brain, but then you're connecting to this external nervous system, full body sleeve. Could you control your whole body that way someday, do you think?
Yeah, I think that that's something that you could see happening in the future. I think that's still a ways away. It's not the ability to stimulate the body. Exoskeleton technology has been around for a long time. Kind of sleeve and orthotic stimulators have been around for a long time. So in the field that you would call neuroorthotics, so brain controlled orthotics that help you move your own body parts, or robotic prosthetics, as we've also demonstrated, work with an arm or a hand right now. So if you, one of our brain-computer interface pioneers, Nathan Copeland, was able to, as a tetraplegic, able to completely control a robotic arm with moving its fingers. And we were also stimulating his brain. So he got sensation back when the fingers touched something. And wow. He was on stage at the University of Pittsburgh, and he shook the hand of Barack Obama, and he felt the handshake as it occurred. And so that's already working. I mean, this technology exists already. It's not an approved device yet, but that's already demonstrated in the research context. And I think not too far off is a hope from seeing that as a device that you could actually see prescribed to patients who have movement disorders. The problem is the same thing you got with humanoid robots. We don't have the machine learning and AI yet to be able to take all that data from the brain and be able to get enough distinguishing intention out of it that you could control all of your body simultaneously. It's two problems. You need a lot of sensors. You need thousands of sensors in the brain, and that's a hard electronics problem. And then the algorithms themselves have to be able to process this neural data, which we don't really fundamentally understand. And so those algorithms need to be much more sophisticated. What you can do is implanted, there's a patient who had this implanted in the M1 motor cortex, and they intended to move their fingertips. So they thought about handwriting. And even though their hand wasn't moving, we were able to interpret their handwriting and write it to text on the screen. And this is the current world record for thought to text this is John Willett's lab at Stanford, of 150 characters a minute. So you just think about handwriting, even though your hand's not moving, and then you're going to see that writing on the screen, autocorrected and everything at 150 characters a minute, which is about what you type at your phone. So you can do it for fingertips. Expanding it to the whole body is going to take more algorithms and sensing.
Yeah. Wow. I know I've heard before, like and I've tried this test before, like if you just kind of like put your fingers on your Adam's apple, larynx, whatever this is, and you just speak in your head, not out loud, it still moves in the same way as if you are speaking. And so people have also been able to kind of like read that and create words from that, right?
Yeah, yeah, and that's there's several different approaches to that. EMG is one where you pick up basically the signals that go to the muscles. You can pick it up on the nerve endings as well, and this works well. A company called Phantom Neuro is doing this, also using BlackRock Neurotech's technology, where they are implanting directly into a nerve and getting the signals that would have gone to that body part. Your brain still generates those signals, and then using that to articulate a prosthetic or an orthotic. So those are different approaches than having a neural implant, where you have the highest resolution data, and it requires that you're still getting those signals on those peripheral nerves. But yeah, both of those are effective approaches, and those are part of a myriad of solutions that are currently being researched, and I think are very promising to help a lot of people with these types of movement and speech disorders.
Wow. What about like the biological complexity of the neural implant? I mean, how have they solved the problem of just like the immune system trying to fight off a foreign body within the body?
I don't think it's solved. It's a little bit of just sheer innovation process and hard work and iteration and some luck. The brain is super good at figuring out stuff that should not be in the brain and getting rid of it, and eventually it will. BlackRock Neurotech's technology has been in human for 10 years plus. That's a really good benchmark, because even if it stops working after 10 or 11 years, usually that's a threshold where patients would be willing to have a surgery to replace or augment that. So that's a good benchmark already, but it's really hard. The brain's foreign body response is pretty strong. If you get too high density in your sensors, then you'll get scar tissue between them and they die. If you don't use the right materials, the brain will eventually erode all of that metal and just deposit it as waste in the body. It's super good at that. But if you use the right materials like platinum iridium for the electrodes, if you have the right kind of insulation, like polyamide, for example, is one you can use to insulate, and then you have the right substrate like silicon, we have found those to be successful and safe in the brain for at least 10 years plus. So I think the materials are looking very promising. Now, scaling that up to many more sensing points so you can get more and more data out of the brain poses its own challenges. But I think the materials we've had a lot of progress on. Got it.
Okay. All right, let's hit on one more crazy thing you've done. And then we've already talked a lot about it, I think, which is the robotics. So I saw on your LinkedIn, you were VP of engineering at a company called Creator. And that company, its mission was basically to create fully autonomous kitchens. Is that right?
That's right. Yeah, we did the world's first fully automated commercial kitchen. And so we were trying to take the restaurant industry, which has been really struggling to keep up with service workers, and to try to automate that and also improve the visibility into the food and the quality of food that you're getting when you're dining out in a fast food kind of environment. And so we built the world's first robot that makes gourmet hamburgers from scratch. And we scaled that up to 5 or so locations. We had several in San Francisco that were retail locations. The food writer for the SF Chronicle gave us a rave review. It was a super fun project. There was an incredibly smart team working on it. The company did not, unfortunately, it was a tough hit to go through the pandemic, and all those locations had to close. And so it didn't quite recover from the pandemic, which was really hard to cross both the VC and the restaurant industry. But I think a lot of that team is still working in the food space, and you can find videos of it online. It was super cool. It grounded the meat to order. It sliced everything fresh. You got to see it all. So there was complete visibility into how the food was made. And we were really trying to improve the transparency of food, and at the same time, improve the experience of people who are working in the service industry, who can be more customer facing and be in more creative roles rather than just sitting over a griddle and breathing in grease-laden vapors and repeating the same task 1,000 times a day, which is pretty soul-sucking.
Yeah, for sure. So were there, at those 5 locations, were there like any human workers at all? Or is it like customer comes up, presses a button, of their order, and then they watch it happen, and then it's like spit out to them? Like, any people at all?
Yeah, we did have human workers in the restaurant. We had prep workers who were getting the food put into the robot. So slicing off the very ends of a tomato, because you don't want that in your food. But the whole tomatoes got loaded and sliced to order. Unpackaging our vacuum tubble beef and putting that into the meat grinder. So there was refilling and a little bit of prep work, cleaning the robot at the end of the day. And the rest of the staff were all customer facing. So you could place orders directly with them. They would bring the orders to your table. You could order from a kiosk. We had a super cool mobile app to customize everything about the order, because robots are highly customizable. But we still wanted it to be a human design centric experience. And so we didn't want to eliminate humans from the process of dining, but we knew that dining was changing, and we wanted to be the shepherds of automation in the space to show that you can do so in a way that is a good place to work, as well as a good dining experience for a guest that isn't devoid of human contact.
Got it. Okay. All right. Well, I want to ask real quick about, like, how does someone end up on basically the cutting edge of like multiple crazy technologies, robotics, brain interface, crazy stuff. Like, and I saw on your background, you like we said earlier, you went to Berkeley, you got your master's there in, what was it? Electrical engineering and computer science?
Yeah.
Okay. I mean, is that like the starting point for people, like people who want to be doing this cool stuff like you? How would they go about doing it?
Yeah, the thing that's not, and I really have been meaning to put it back on LinkedIn, that's not there, is I spent a lot of time at community college, and before that, vocational school. I went to culinary school for a year. I did IT school for a year before going to community college. I spent 4.5 years at community college at Santa Monica College, where I could not recommend that more. The education quality was great. I didn't know where I was going. I didn't know what I was going to do. And that was a very safe space for that. So, education for me has always been something that I've resonated with very strongly, and has one of the first kind of North Stars that I ever had. And, for me, it was a very non-traditional, like I didn't just go immediately to a 4-year school, get the master's, went straight into the career that I thought was going to be the best job. I think that you got to be passionate about the thing you're doing, and not worry about making every decision correctly from a standpoint of a career. I got started later in my career than most people. I've spanned everywhere from software development to IT to robotics, and in leadership now. And so the one thing that has been the common thread throughout that is just continue to be growth focused on how you grow yourself and learn. Be as receptive as you can be to feedback and seek it out. It's a really ambitious goal to say, I'm going to go work on robotics or brain computer interfaces. Just start with the first steps. Can you rapid prototype something? Can you play around with it? If you're in school, can you build a school project about it? Is there a meetup? San Francisco has hardware startup meetups. There are brain computer interface meetups, virtually and in person. Just start to engage with communities more. Start to learn what you can. Find the YouTube videos that are cool on the topic. Take first steps to start to dive into the space, because you may not realize where you're going to have the best potential to contribute, or you may realize, hey, this isn't actually the thing I want to do. But do it in a more iterative, kind of agile way. Just experiment, try something new. Imagine, hey, what would it be like if I was a roboticist? What would it look like? And how could I engage with it? And just start off in those small pieces. And then as long as you're growth focused, seek out feedback and are open to it, those opportunities will eventually present themselves to you.
I love it. Awesome advice. Jeff, thank you so much for joining me in the Lion's Den today. I learned a ton. Super, super stimulating conversation. So thanks for coming, man.
Oh, my pleasure. Thanks for having me, Nico.